Okay, let's get started. It's 8:04. I just put a chat note. Before we get started with nearest neighbor, I want to do a very small sort of jogging your mind exercise. Um, a very small, you know, sort of quick quiz. Um, we learned about 5 ML algorithm classes so far. These are mentioned in my message. I have given 2-letter abbreviations to each one. Okay. Um, now, I will ask 2 or 3 simple, direct questions about this. And into the chat window, if you could please type the technique that fits the question that I'm asking. The question I ask will have, only one technique will fit it. And if you could please type its abbreviation. So you just need to type 2 letters. Um, and we will, look at the first 10 or 15 for first few answers, and then we'll move on to the next question. It's a very, very quick refresher. First question. There is only one quantity to be predicted. Looking at its historical values, we want to predict its future value. What technique do we use? Yes. Okay. Many said time series. A couple said regression. Couple of you said regression. Regression can work if there is one independent variable and one dependent variable. There has to be a different independent variable and a different dependent variable for regression to work. So there are at least 2 variables needed. Whereas time series will work with just one. If there's only one thing whose future you wanted, the future values of that you want to detect based on its past values, it is time series. Okay. I think all of you either said time series or regression. Nobody said any other. Okay. Now, next question. Yeah, Mr. Bhaskaran.
So, yeah, I also answered time series, but interesting question. If we model the time itself as the x-axis,
Yeah.
can't we convert the time series into a regression model?
Yeah. If there is if your quantity that you're predicting is such that it can be in a simple mathematical equation, you can plug in time and you can compute it. Yes, you can. You may need to do some, intelligent feature engineering, saying, for example, I want to predict the temperature, okay, and in a given region. So I have only one variable, which is my date and time. And based on the date and time, there's cyclicality in the way the temperatures go. So my, I can, in time series, I may be able to catch the cyclicality, the seasonality of all of those in a time series equation. Remember, a time series equation will be much more sophisticated than a linear regression equation because it has, the trend term, the cyclicality term, the seasonality term, and the random variation term. So you may be able to do a better prediction with time series, but you're right. It is possible if you have an outcome that is predictable with simple linear function of time, then you can use time as an independent variable. Interesting thought. So next question. I have a satellite image and I want to measure green cover in it. I'm comparing multiple cities. I have satellite images of all, and I want to compare green cover. What technique? Perfect. All correct answers so far. Clustering. clustering tip, if you want to go a little bit deeper, probably density based clustering. We talked about k-means, k-meanoids, which are spherical clustering methods. We talked about hierarchical clustering, which is either agglomerative or divisive, we said. And then we talked about density based clustering. Very likely density based clustering is the answer. Okay. Mr. Shibaba said classification. Uh, uh, mm, Classification, you need to have a, you know, if the problem definition is how do I discover that something is a green cover, then you may have the intensity value of that pixel, the neighboring pixel values, etc., based on which you predict that a pixel is green cover pixel or not in the satellite imagery. That will be a classification problem. But if I want to measure green cover for multiple cities and compare them, the easiest way, I don't even need to have ground truth. The easiest way is to combine all the green pixels into a cluster. Based on the color of the satellite imagery, I can just based on the raw pixel values, I can do density based clustering and get all green cover. The green cover, why density based clustering? Because the green cover may be in different shapes in different cities. New York will have a clear Central Park, whereas London might have a very different type of greenery distribution. Tokyo might have a different one, so on. Okay, great. So let's move to the third and last question. There is a I'm looking at purchase of computer peripherals by users. So I run a store which is selling, laptops, cameras, speakers, so on and so forth. And I want to find out the relationship between laptop sales and peripheral sales. What algorithm would I use? Fabulous. So a lot of you have answered association rules, and that is the correct answer. Some of you have very interesting answers. One said collaborative filtering. Collaborative filtering is a recommendation algorithm. You are absolutely right, Mr. Krishnamurthy. CF can be used. On when you are the purpose of collaborative filtering is to increase sales. The association rules can be for a multitude of purposes. They could be for bundling, they could be for merchandising, promotions, discounting, so on, predicting customer behavior, etc. Whereas the purpose of recommendations is to increase cross-sell, upsell, and increase the sales. So if in collaborative, using past data, you can discover in collaborative filtering that everybody or people who bought a laptop are likely to also buy a peripheral. If you prepare the data in a way that you take away the time axis, because somebody may have bought laptop on a certain date and after 15 days come back to pick up a speaker. So if you take away the time axis and look at a larger basket of what people have bought, and from that, you're predicting that there is an association between buying a laptop and buying a speaker. So anybody who has bought a laptop, I want to recommend them a speaker on day one. Definitely, you can use collaborative filtering. But I hope you're able to see that collaborative filtering is only for doing that recommendation, whereas the association rules much more easily, but for smaller stores, much more easily they can identify such patterns. And then you can use it for upsell, you can use it for merchandising, you can use it for discounting, bundling, whatever. So they both are, we discussed both the techniques on the same day because both of them are solving a related problem. Both of them are looking at market baskets and in a unsupervised way and finding patterns. That's why we discussed both the methods on the same day. If for this particular association rules would be the first technique that comes to mind. Some, CF can also be used. CF is more complex, CF requires more compute than association rules, but association rules do not scale. So depending on the size of your shop, you will decide whether to, which technique to use to discover that association. And there was also a regression that is mentioned by Mr. Chan for this. And it is, we are now, this is actually a subtle but very interesting point. If I have a laptop purchase on the x-axis and peripheral purchase on the y-axis, what are we plotting? Are these, are these continuous variables we are plotting, or are these discrete events that I purchased a laptop? That's all I know, that it has been purchased. There is no quantity that I have purchased. For somebody who purchases, let's say we are looking at wholesale purchases and say somebody who purchases 100 laptops will buy 400 peripherals, then there are continuous values that you can actually plot and you can try to fit a trend, a linear regression trend to it. But what I have said is simply that they have bought a laptop. We want to discover whether they will buy a peripheral. These are discrete attributes. So if you remember, the feature values, that is the independent variables, are continuous both in linear regression and in logistic regression. The logistic regression does accommodate some discrete values also, but you will need to first assign numbers to them, assign numeric codes to them. Here, when we are talking only about discrete features, we need to use a different method, either AR or CF, collaborative filtering or association rules. Okay.
But my view is that from a marketing point of view, people may want to know the dependency. So a dependency using regression method may have some value to it. I might be wrong.
I'm sorry. Would you kindly say that again? I missed what.
I was just thinking that from a marketing point of view, people may want to know the dependency from these two for these two variables. So a regression analysis may provide some insight into that dependency.
Okay. So then I would define the problem. Let me define the problem in a way that it is suitable for regression. I'm looking at how much money a customer of mine spends on peripherals. So the quantity I'm trying to predict, my dependent variable is dollar value spent on peripheral purchase. And I, as a domain practitioner, I come up with with a list of independent variables that may be impacting that dollar value of peripheral purchase. One, the value of the computer that they have purchased, the number of days since they have purchased a computer, the value of the peripherals that they have already purchased, and the number of days since the last peripheral purchase, the age of the person, so on and so forth. I may define some independent variables, and I have a continuous variable that I want to predict. In such a case, you can come up with a regression equation which will give a weightage to how important is buying a laptop to buy a peripheral, or how much determinant the laptop purchase is on the amount of money that the person will spend on peripherals. So you're right, it's the same business problem we are solving, but by the way we define the business problem, the choice of the method is changed. It has changed from association rules or collaborative filtering to regression because I changed it to continuous variables. Would you agree with that, Mr. Chan?
Oh, yes, I agree. Thank you.
Okay, thank you. Mr. Shibaba says most e-commerce companies use market basket analysis, identify purchase patterns by finding products that are commonly bought together. This helps the consumer purchase patterns, so they can adjust that. Yes, absolutely. Thank you, Mr. Kannan.
Professor, is it right to understand that association rule will be the first step where you have a purchase sequence or family method, whatever you talked about earlier, then move on to collaborating filtering where the content and context will come, and then we pre-compute to recommendation? Is that sequence right in whatever you're saying?
Um, the association rules and collaborative filtering are not sequential. You will choose one based on the size of the organization. So if you are dealing with Amazon, you would not apply association rules because simply there are too many rules to filter. So you'll directly go to CF. So that is not a sequential sort of evolution. The third thing you said is understand the relationships. Yeah. So to
Pre-computed recommendations.
to discover co-occurrences or to sort co-occurrence probabilities, sort co-occurrence potential, you use collaborative filtering, association rules, and so on. To discover relationships between independent and dependent variables, you use filtering. You use regression. So you will define the problem upfront, Mr. Kannan, that I'm interested in discovering what variables have a bearing on the amount of money somebody spends on a video game. Okay, I'm interested in finding what variables have a bearing on that amount of money. Then relation is what I'm searching for. When I'm searching for a relation, I look at regression as a solution. Of the methods we have talked about so far, we'll talk about more methods, then the repertoire will increase. If I'm not looking for a relation, I'm looking for a co-occurrence. Somebody who has seen this has also seen this, so on. Then I would look at AR or CF. Right? If I'm looking at forecasting a single variable, then I would look at TS.
Okay.
If I'm looking at a geometric, shape of points, that these points are all occurring together, these points are distributed all over the place, etc., then I would go to clustering.
So if I'm using an agentic AI, this will be last what you said will be the first step for agentic AI for recommendation. Would that be right?
Yeah. Clustering, when you don't know what patterns exist in your data, clustering is the first step. Whether it's agentic AI or regular ML, clustering is a good place to start if you don't understand your data yet.
Thank you.
Yeah, thank you. Okay, so we are done with 5 techniques. Let's now leave them. Clear your mind of these 5 techniques and let's go into the next technique. Clearing is important because we should not connect concepts from one of the previous techniques you studied into this. So leave the previous techniques aside and let's get to the KNN. Now, KNN belongs to a group of techniques, a group of learning methods called lazy learning methods. The word lazy here just simply shows that we don't build a model. We do nothing until a test sample arrives. So somebody came and gave us 1 million data points with proper features, all collated, curated training data. We just sit with it. We do nothing until the first test case arrives. And only then we start our is the characteristic of lazy learning methods. Of the class of lazy learning methods, K nearest neighbor is one technique. These nearest neighbor methods have also been called by these names: instance-based learning, case-based reasoning, exemplar-based learning. There are subtle differences between them, but at a higher level, from a let's say 5,000 meter level, when you look at them, they are almost the same method. They are all very similar to nearest neighbor. So we won't be studying these methods separately. We are bundling that into nearest neighbor. So let's first find out what lazy learners are. These are supervised methods. So you have been given 1 million data points with class labels, but you have no interest in working until the test sample arrives. Okay, so it's supervised methods. And we wait to see the test sample before doing anything, before building a model. The others, like regression guys, as soon as the data came, they ran their, regression they ran their regression engine and came up with their equations. They're sitting with it. You remember stage 1 and stage 2, where stage 1, you build the model. Stage 2, you use the model to infer. For lazy learners, there is no stage 1. They just receive the data and do nothing. They directly go to stage 2. And they do all their computation at stage 2. So they wait to see the test sample before learning anything. Of the lazy learners, k nearest neighbor is the most known method, most popular method. There are others too, which are called, which go by the category of local learners. So you can have a local regression, local SVM, etc. And I'll tell you how they work. Okay. So there are multiple lazy learning methods. Since they're doing nothing with the training data, they really don't suffer from drift. They can trivially adapt to evolving training data or drifting training data. Drift is where your training data distribution itself, underlying distribution of training data is changing over time. Let's say because of the war, the underlying, if you were looking at some application in, oil and gas distribution during the war time, with every passing week, the nature of the training data was changing. So such a thing is called drift, and lazy learners, because they do nothing, can trivially adapt to training data changes. They're suitable for problems where one cannot assume that training and test samples are drawn from the same distribution. This is their primary advantage. If you are having a problem where the data is evolving so rapidly that you do not know the distribution, you cannot make an assumption that tomorrow looks like today. I said this while I was introducing machine learning in that session, in the second session, that the underlying key assumption of machine learning, all machine learning methods, is that tomorrow looks like today, that you can build some model on the training data and it will apply to test data. If that assumption does not hold for you, for example, today's job market, if somebody is building an ML model for today's job market, I would seriously wonder if job market after 3 months will look like job market today, or job market after a year would look anything like the job market today. So in such a case where data is rapidly evolving, lazy learners do well because they don't depend on building a model. Okay. And for k nearest neighbor, selecting k is an important step. And there are heuristics that people have built for this. And there are ways in which k can be determined. Okay. So first, let us look at the nearest neighbor rule. And through this, I will also explain the local learners. I'm just doing a quick time check. Okay. The nearest neighbor rule, let's say these are my points. So there are two classes, red and blue, or circle and square. And they are in 2 dimensions. So there are, we are able to plot them on one screen. Let's say the black thing is the query point. If k were 1, what we do is for this black point, we will compute the distance from the entire training set. So they gave us this training set, blue and red points. We are lazy learners. We just sat with the data. We arranged it into they gave it as a matrix and we left it. Now a test sample arrives. So we are already in stage 2. Inference has begun. For this test sample, the first thing we do is we go and compute its distance with all the training data that has been given to us. We sort those distances. Okay, how do we compute distance? Because we are given a feature space. So, we can, in that feature space, we can do when we were discussing unsupervised learning, when we were introducing unsupervised learning, we talked about, Euclidean distances, multiple types of attributes, distance computation, so on. And we also talked about curse of dimensionality, where distances don't make sense in higher dimensions. All of that we have already covered. So we know how to compute the distance of a new point from all existing points. And then we sort the distance. Distance is a number. It can be sorted. So the closest one, lowest distance, if k equals 1, I simply assign the class of the nearest neighbor to this black point. So I will call the black point blue. It belongs to the blue category. That's how one nearest neighbor would work. A 3 nearest neighbor, I would compute the distance. Computing the distances is the same, no matter what the value of k is. The number of, after sorting, the number of points you would take, number of nearest neighbors you would take is k. So you take 3 nearest neighbors here, and you take a majority label in that. So you're taking an odd number so that majority can be taken. If there are 2 classes, you take an odd number. If there are, k classes, nearest neighbor will work very well for non-binary class problems also. It's not, unlike regression, it does not need only 2 classes. Regression works only for 2 classes. You saw that we can only draw a line, so there are only 2 sides to it. So if we are given a multi-class problem to regression, we apply, one against the rest. You remember yesterday we were talking about this. So class 1 against class 2 plus 3, class 2 against class 1 plus 3. Like that, we will build 3 different regression classifiers. Whereas nearest neighbor, you don't need to do that. Nearest neighbor can handle any number of classes directly. So if there are, n classes, then you would at least set k as n plus 1. So that there is a, you would set a number of neighbors, which is at least as many as the classes. Because in case, all points are of different classes, which is unlikely, but possible theoretically, then also you can find the majority label. Essentially, you're looking for a majority label. In this case, it's only 2 classes, so the majority label is red. So the black point will be called red in a 3NN, whereas if we were using 1NN, the black point will be called blue. So our class assignment or class prediction might change depending on the value of k that you're using. If k were 7, then probably all the points that are in the picture except this last one may be the 7 neighbors for this black point. And there, red is the majority label. So red color will be assigned in 7 and n. The value of k is chosen upfront. So you're running either 1NN or 3NN. You're not deciding that dynamically. Depending on what KNN you are running, what your value of k is, after sorting, after finding distances and sorting them, you will take those many neighbors. This is how KNN works. Very, very simple algorithm. We'll talk about the computational complexity and all that later. But conceptually, I hope it's very clear to you how KNN works. Now let's assume that K is 7 or 11 or 13, some large number, some larger number. Let's say K is 11. We have 11 neighbors. Now these 11 neighbors, a simple way is to um, do a majority rule. Which class has more points? But if you want to be a little more sophisticated, because you have 11 points, what you can do is you can build a little regression model, a local logistic regression model for those 11 points, and classify the black point according to that logistic regression. So when your data comes in, you're finding the neighborhood of the current point, which test point which has arrived. You're finding out a local neighborhood. In that local neighborhood, which consists of 11 points, you can build a regression classifier and use that classifier to classify this. So not just based on distances. Why would I want to build a classifier? Because, if it is a higher dimensional data, then distances are unreliable in higher dimensions. We suffer from the curse of dimensionality. So nearest neighbor does not work too well. Distance computations do not work too well in higher dimensions. So after finding a local neighborhood, I may be better off to not depend on the distances again, but build find the decision surface and find which side of the decision surface this new point lies on, instead of looking at the distances. I hope in your mind's eye, each of you is able to see what I am seeing, which is a bunch of points in higher dimensions. A new point has arrived, and I have a local neighborhood which has some distribution of these 11 points. And there could be a linear separator, there could be a non-linear separator in that little group of 11 points. And depending on which side of that surface this black point falls on, we assign it a label. That is called a local classifier. So when in lazy learners, we said there could be a local SVM, a local regression, a local neural network. These things are possible. All of them are lazy learners. Because we are not building a global model at all. We are only doing local models. The advantage of local learners is that you don't even need to wait until you get the test sample. You can do some pre-processing and build a lot of local learners by subsetting the data. You can build a lot of, for example, I can grid the data. Okay, I'm given a data in, let's say, 2 dimensions. For simplicity, let's say 2 dimensions. I do X lines and Y lines and grid it like a graph paper. Okay, like I grid that into smaller squares or rectangles. And inside each square or rectangle, if there are more than n number of points, more than some 11, 10 points, let's say, I build a local classifier upfront. I have not even received my test sample yet. And when a test sample comes, I simply find out what grid it belongs to and run that local classifier. If there is no local class, if there were not enough points there, then I would combine it with neighboring cells and then build a local classifier on the fly. So it is possible to do some pre-processing in the local learner space. For k nearest neighbor, that is not possible, but both are, the idea is overlapping. I hope you're able to see that essentially when a new point arrives, we find its neighborhood, local neighborhood, we find the points in it. Either we use the majority rule in KNN, or we can build a small local classifier and classify it. Okay. Let me take Ms. Raguraman's question, then I want to add one more point.
Thank you. When we build a local classifier, it would be a model for each of the classes, in this case, 2 different regression models, and then compare the 2, or how does it work?
Yes. In regression is a technique that works only for 2 classes. So you need to build, if you have K classes, you have to build K regressors, right? K equations, K alpha plus beta X type of things. You have to build K of them because regression necessarily works only for two class problems. So that's a characteristic of the method. SVM is also a two class method. So you will need to build local multiple SVMs. Whereas if you are using a neural network locally, then you can, or a decision tree, both of them accommodate any number of classes. So you can take the local points and build a small decision tree that only one decision tree would do. So it depends on the technique.
Right, right. Thank you.
Okay. So we said take a local neighborhood and either use the majority rule, which you do in KNN, or you build a local classifier, which will also be a lazy learn. Now, I hope all of you are able to see that the bottleneck here, one big bottleneck here, is computing distance of the new point with all other points. So if my training set consists of 100,000 samples, then I need to compute 100,000 distances for this new point. For every new point that arrives, I have to compute 100,000 distances if I'm doing this in brute force. There are ways to speed this up. And for example, the grid, I said you can locate which grid the point is falling and only look at the grids around it to find its neighbors and not see the entire data set. Now it's possible I can construct examples where this approach will fail because the nearby grids may not have a nearest neighbor. Your nearest neighbor may be in a faraway grid. So this grid approach, while it will speed up many of the, for many of the test points, it can speed up computation. It may provide a wrong answer for some of the test points. In fact, you can construct adversarial examples. You can construct examples construct the data set in such a way that your grid-based nearest neighbor identification will fail. So these are called approximate nearest neighbor methods. Approximate nearest neighbor methods, use heuristics or use intelligent tricks to reduce the amount of time they need for distance computation. Because nearest neighbor requires distance computation, but approximate nearest neighbor methods, make assumptions and reduce significantly the time needed. So they speed up the, computation of nearest neighbor, or the speed, because they have not done any model building. They're doing all the computation at inference time. Nearest neighbor is typically a slow technique. So to speed it up, we use approximate nearest neighbor, where we use some smart tricks to reduce the time, reduce the number of points with which distance needs to be computed for a new sample. There are also methods that are called condensed nearest neighbor or reduced nearest neighbor, which try to shrink the number of data points with which distance needs to be computed. Condensed nearest neighbor, reduced nearest neighbor methods. There are a bunch of such methods. Their purpose is to cut down the time that it takes to compute distance. That's the primary bottleneck of a nearest neighbor method. Time that takes to do the inference. Mr. Bhaskaran.
Yeah, in the grid-based approach, if you find that a point is not closer to any of the existing cluster of points, isn't that an outlier?
There are no clusters, sir. There is no cluster here.
Okay, yeah. What I mean by cluster is like the group of points that are existing, right? So you are saying that in the grid-based approach, there could be cases where an incoming point is not closer to any of the points in the grid. It may be in the faraway grid, right? So in such a case, can't you just classify that as an outlier and reject that? Why do we need to even put a class for that?
Because because you're using it, let us say, to assign some class label to a new customer and things. You can, of course, you can always say this is an exception, I can't do it, and give it to a human being to figure it out. But it need not always be an outlier. That's why I said we can construct data sets, legitimate data sets, where grid-based approach can provide wrong answers. It need not be outlier. It need not be an outlier. So for example, let's say if I have a uh, point here, somewhere here where my mouse pointer is now, this one here. So if I divide, this may, I'm not sure if it will fall under this grid, or if it will fall under this grid, or if it will fall under this grid. And depending on which grid it falls, the calculations will be different. So it's not hard to construct adversarial examples for approximate methods like these. They're still useful. They're useful for 95% of the points, but you cannot ignore the other 5%, saying that they are outliers, because they may be legitimate points. Yeah. So in that case, I mean, I'm not saying this, I'm not presenting this as a problem. I'm just analyzing that, okay. Ms. Raghuraman, did you have a question?
Yes, Professor. Uh, Instead of, uh, putting up a grid or developing a grid before we receive the sample point, can we kind of adjust the grid scale after we receive the sample point in a way that we will be able to get more number of nearest neighbors?
Absolutely. Absolutely. I think you can. And if I'm not mistaken, there are authors that have looked at dynamic grids, which are calibrated quickly after a test.
Right.
The trick is to do it fast
Correct.
Fast
Yes,
inference.
yes. Maybe have multiple options available and then just pick up the one which gives the maximum number of nearest.
Exactly. I agree. So let's move. Why, despite its simplicity, KNN actually works well in practice. One of the first use cases for which KNN really did well is the digit recognition problem. These are, people. There was a time when people were writing letters, and that too, writing the address by hand. And there were, US Postal Service had a nice large data set that they formed of people writing zip codes, and they wanted automatic zip code recognizer, handwriting recognizer, which will read out the zip codes from envelopes and or boxes, and sort the boxes accordingly. So automatically sort packages based on the zip code. The core of this was being able to recognize that this is a 2 and this is a 6. And that was a machine learning problem. So they started with each digit was a 28 by 28 pixel. So you cut this, you get a little square in which this 2 sits. And that is a 28 by 28. They took 28 by 28 pixels. And that multiplication is 784. So each digit is a 784 pixel shape. And this is a black and white image. So you have either ones or zeros. That is 255 or 0. That's the pixel. Well, in each pixel is either lit or dark. If you have grayscale, then it is some number between 0 and 255. So they took 60,000 training samples of, obviously there are 10 classes, which are these 10 digits. Maybe there is one class which is unrecognizable. So total of 11 classes. Okay. So 60,000 training samples, 11 classes, 10,000 test samples. So you had a total set of, 60,000 plus 10,000, 70,000. So that 10,000 is kept aside as a, test sample. And you report the accuracy of that. When that is done, these are some results that you can see. K nearest neighbor with, firstly, the linear classifier. They built the linear classifier from a neural network, not from a regression. It is possible. Neural networks are built out of these things called perceptrons, which work very similar to regression. Individual neurons work very similar to regression, although they have a few extra things there. So they used perceptron-like structure, which gave them an error rate of 12%. What does that mean? 12% of the 10,000 samples were misclassified. That is, 1,200 samples were misclassified. When they used K nearest neighbor with Euclidean distance, whenever you're mentioning that you're using a K nearest neighbor, you have to say what K is, and you have to say what distance measure you're using. So here they used different types of Ks, typically 5, 7, 9, 11, like that. K nearest neighbor with a Euclidean distance gave them 5% error rate as opposed to 12%. So there is a steep increase, steep improvement when they moved from one layer neural network to simply doing K nearest neighbor, a lazy learner. And when they took a de-skewing step, they took the digit and removed the skew. Skew means that you may and the image may be like this, but it has a certain orientation. So by looking at the orientation of pixels, you can de-skew it. It's a simple mathematical correction you can do to the image. So when you de-skew it and use the same Euclidean distance, the error dropped further to 2.4%. To 2.4% of 10,000. So 240 images here that are misclassified. And K nearest, same K and N with Euclidean distance changed to something called tangent distance. And the pixel maps are in 16 by 16 instead of 28 by 28. They did even better. Then when they change the distance measure to another shape context matching, you see a further reduction. So you actually bring, if the error rate is 0.67, means that the accuracy is 99.33%. So you have excellent performance by K nearest neighbor by choosing the right kind of distance measure and the right kind of K. Okay. So this is one practical example of what you can do with K nearest neighbor. It's an older example. There are many recent systems that are built on K nearest neighbor. It continues to be a relevant technique. And I won't talk about the others because we have not yet studied SVM or radial basis functions or deep learning networks. These are deep learning networks, LeNet and boosted LeNet. So we'll get to them later. But it's interesting that K nearest neighbor actually gives a comparable performance as a boosted LeNet, which is a deep learning network. This is 7.7 error. 0.7% error. This is 0.67% error. It's actually better than that. So KNN does well here. Mr. Dutt?
Yeah, I was about to just ask you that in terms of, since this is such a sensitive thing and there is a possibility of misdirecting the mail, what was the degree of confidence that this actually is going to give me the right mailing pin code?
Yeah. Eventually, the method that got implemented by US Postal Service was the LeNet, Mr. Dutt. This LeNet was, developed in University of Toronto. And this was in 1997, if I'm not mistaken. And eventually that was the network that was used by US Postal Service for in its first implementation deployment of this system. So it was actually a fairly dependable recognition of these digits. But KNN itself doing doing well is a sort of pat on the back for KNN, because we are not, I mean, in Lenet, we are discovering features. In KNN, we are using raw pixels or, something that the distance metric is, some way that the distance metric is comparing between raw pixels. So with raw pixels getting to this kind of accuracy is a pat in the back. Yeah. But to answer your question, there was a practical system that was deployed and worked well. And you can actually, you can look for US Postal Service digit recognition with ML and you will see multiple papers on this.
Okay. And you mentioned that what was used was Linet.
Lenet. This one, the last one here, Lenet.
Oh, okay, okay.
Yeah.
Okay.
Okay. Yeah, it was named after a person that was, this was, like I said, a Toronto team. Okay, the algorithm, I think, is very clear. All of us, I mean, we already talked about it. Store all input data in the training set. For each instance, you search for the k nearest instances to that and use an appropriate distance measure. And then each, compute each class, you take the majority class, essentially. That's what this whole thing is. Majority class is being computed, is being taken. So if red and blue are the classes, red has 3 out of 7, then its confidence is 3 by 7, whereas the same is 4 by 7 for blue. So whichever has the highest confidence, that is 4 by 7, is picked. So overall, this is just saying take the majority class. Okay. And some observations about KNN as a method is that if you have noise in your data set, then your nearest neighbors will be wrong. They may have the wrong labels, or even your distance computation could go wrong. So noise affects KNN. KNN can overfit. This is the same statement as before, because it doesn't differentiate between noisy instances and real instances. KNN can give, better accuracy on the training set, but fail when we go to test set. That's what overfitting means, right? And it can be impacted heavily by missing values because you have to compute a distance. And, if an attribute is not present, then you're unable to add that component of the distance. So you are actually, you're computing the wrong distance. Hence, you'll get wrong neighbors. Imputation of values, missing values is one possibility, but imputation itself, you typically uses nearest neighbor type method, so it may be self-defeating. If you don't know what imputation means, don't worry about it at this time. It is essentially filling a missing value from the other values. So if, I don't know the height of a particular student, but I know that this student falls in a cluster of students, I can look at the heights of all of them and take an average and fill it as the height of the current student. That is what is imputation. Okay, filling a missing value by taking neighboring examples and an average of them. But there itself, in the definition of imputation, I'm saying you take neighboring examples. So again, you're using the concept of neighbor, which is the nearest neighbor, which is critical to nearest neighbor. So imputation could be self-defeating. You could also have, your distance may be computed using Euclidean distance or weighted Euclidean distance, where every dimension is given different amount of importance. That is what is called distance weighted nearest neighbor algorithm. So for example, if the test sample has 5 neighbors, then the importance I give to each neighbor will be inversely proportional to its distance from the new example. So if something is very close to the new example, then I'll give it high weightage. if something is far away from the new example among the nearest neighbors. So let me go back to that screen just to illustrate what I'm saying. Here, let's say if you take these, there are 3 neighbors, but this blue point is much closer. So I'll give it higher weightage. I'll give the distance higher weightage. Whereas this one is a little far away. So the weight for this red example will be less than the weight for this blue. And this red will get the least weightage. If that is the case, maybe since this blue has gotten higher weightage, the final class may become blue. Although in majority, it would have been just red. If this blue were very, very close to this, since the weightage is inversely proportional to the distance, the blue may get a very high weightage and blue can become the label of the new point. That's what I mean by distance weighted nearest neighbor. Okay. This part is, let me just put it in a, theoretical guarantee. The one that says theoretical guarantee here, this is an important one. With nearest neighbor, we know that the error that one nearest neighbor produces on a data set, the error that one nearest neighbor produces on a data set is no more than 2 times the maximum error or the best error that you can get for that data set. Let me say this again. This is a tricky thing because we have not talked about this concept before. Every data set has a, an extent to which it can improve error. You can juice a data set only to a certain extent. After that, you run out of that juice. You cannot do better than that on a given data set. If you want to do better, you have to get more data, or you have to remove some data, or you have to change the data set. If your data set is fixed, then there is theoretically a best possible accuracy you can get to with that data set. That theoretical accuracy is called that theoretical classifier, which gives the best possible accuracy. It doesn't exist in practice. It's a theoretical concept. That is called Bayes optimal classifier. So on a data set, you cannot do better than that error. Okay. Now, how do you find that? Because it's a very useful thing. When you give me a data set, if I can say to you that, look, with this data set, I cannot get more than 94% accuracy for your sales forecast, then that's a fantastic thing to tell a customer, that you cannot do better than 6% error using this data set. But how do we know this? How can we tell? You can tell because one nearest neighbor has a property that its error will not be more than twice of the Bayes optimal error. So if I run a one nearest neighbor on a data set and the error that I get is, let's say, 14%, then I know that my Bayes optimal classifier cannot have less than 7% error. That is half of one nearest neighbor error. So if my nearest neighbor gives a 14% error on a data set, I know that with that data set, I cannot do better than 7% error. Okay. So I may go and try other methods to see if they will give me between 14 and 7% error. But K nearest neighbor is still active. People like the method partly because of this. Just by running a K nearest neighbor on a data set, I can get some idea of what is the best I can do with this data set. I have simplified it a little bit for you. I don't want to get into the equations of the theoretical guarantee. It has some math behind it. I simplified it, but I think what I said is accurate, that if you know that your one nearest neighbor on this data set is producing K% error, you can be sure that no classifier can go below k by 2% error. Okay. Then as the complexity of the space grows, accuracy comes down and you need more data. Complexity of the space grows. That is, as the data distribution becomes more complex, you need more training data. With less data, nearest neighbor will be inaccurate because you're looking for a nearest neighbor, and if your data is sparse, your nearest neighbor may not mean anything. Increasing K can reduce the overfitting. I already mentioned this. Because you are increasing the neighborhood size, you're not basing your decision just on one noisy point. You can actually look at multiple neighbors. Hence, you will be less prone to being affected by noise. You will be less prone to overfitting. So increasing K reduces overfitting. And there is an optimum K for a given data set that you find out through empirical experimentation. So typically it follows a hockey curve. So as you increase K, your overfitting reduces and your validation test accuracy increases, validation error decreases. So let's say error drops up to some point and then grows. The lowest point, that hockey curve, lowest point is the best hockey curve or elbow curve, it's called. The lowest point of that is the best K. So you do experimentation to find the K. Okay. I'm not hand waving. I'm just trying to stay at a summary level without going into the actual techniques used and discussing it. It will take much more time, and it's also not needed. Determining K is important in nearest neighbor, K nearest neighbor, and the way you determine it is by looking the elbow curve, and you construct the elbow curve by experimenting with multiple Ks. So it's an empirical thing. These are the observations. These are some observations. I hope all of these are clear to you. This here, I'm just continuing with these observations, but in terms of computational complexity, nearest neighbor is expensive. We mentioned this. At the inference time, for every test sample, we have to compute distances. And the way you can reduce that expense is by pre-sorting training examples into data structure, specific data structures. Grid is the simplest one, but there are things called KD trees, which really help in terms of fast calculation of distances. K-dimensional trees for computing distance. Compute only approximate distances, not the actual distances. And LSH is one technique that does that. Remove redundant data. I have already mentioned condensation, condensed nearest neighbor, reduced nearest neighbor. These are methods to decrease the number of samples with which distance needs to be computed. And nearest neighbor has a high storage requirement because it must store all the training data. If you have a 10 million data points, you have to store all of them during the inference time. And one way to handle this problem is through condensation. You actually shrink in condensation, in condensed nearest neighbor. The core idea is, see, I may have 10 million points in my raw data, but I may be able to, there may be many points in that 10 million that are not influencing my neighborhoods or distance computation at all. They may never come into my distance computation. What I mean by that, let me just show you. I'll go back to this two clouds of red and blue points we had. Yeah, here. Let's say, let me draw this. let's look at, these points in the middle here. Some points are there in the middle here. These guys are probably not going to influence any new points decision because they occur at the core of a blue cloud. Even if you remove that core, still every new point will be classified correctly because this blue cloud around it is still there. So anything that would have been classified blue before the removal of this set of points will be classified blue even after removal of those points. Likewise, everything that is classified as red will continue to be classified as red. So this internal points, this core of a cloud, has really no impact on the classification. So in condensed nearest neighbor, we identify points like these and we take them out. So your original raw data set may be 10 million points, but after you condense, you may be left with 200,000 points because you have removed the, the points which are inside clouds of the same color. Okay, clouds of points of the same color. Is this making sense to you? I hope it is. Yes, Mr. Agraman, yes.
We'll completely remove those points, or we will replace it with some average point or something?
No, we'll remove them because, you remember in nearest neighbor, we have to store all the training points in order to compute distances. So we are saying that let us not store those points at all. Because why store those points? They're not influencing the future label assignments in any way because they're occurring at the core of a blue cloud. So even if you take that away from your storage, it makes no difference to your future classifications. So we remove the redundant data. This is what we're calling as redundant data. It is redundant for the purposes of determining the class label. That data, of course, is needed somewhere else. You're forming a data mart. You're taking a subset of the data, putting what you need for your machine learning modeling. All we are saying is when you run condensed nearest neighbor, it takes away the data that has no impact on the future classifications.
Thank you.
Okay, and the last one is curse of dimensionality. I have already mentioned curse of dimensionality. Clearly, nearest neighbor gets affected by that. So that's all I would like to say for today. We are done with what we wanted to do for nearest neighbor. We'll take on decision trees in the next class. It's not a problem. We will be able to handle, all the topics we wanted to cover. So don't worry about it. But I don't want to hurry through decision trees. Anyway, we are out of time. We are 2 minutes past our class time. There's a message. Okay. Thank you, Mr. Shibaba. Sorry? Mr. Kannan, yes. Thank you. Thank you, Ms. Rajeshwari. Mr. Kannan, yes.
Doctor, I have couple of questions.
Yes, sir.
I have a couple of questions. One is on weightage, which I wanted to understand, either it be B1, B2, or B3, whatever you're talking about, or in the case of K neighbor, how is the weightage assigned? Say, like
Weightage
for
for a
example,
point
we
or
had
weightage for a dimension?
a dimension. Let's say
Oh.
age. We are taking age, whether it's male or female. Okay, how does that weightage get assigned? I'm not able to understand.
In regression, right? So if it is beta 1 times age, how do we determine that beta 1? Correct?
Yes. How much weightage do we assign it for the final result?
So it's a search. It's an optimization problem. So you will start with a initial assignment of beta 1, beta 2, beta 3. Let's say if it's a multiple linear regression, you have 3 dimensions. So you will start with some starting value for beta 1, beta 2, beta 3. It is a point on your error surface, that beta 1, beta 2, beta 3.
Yes.
Right? So what you do is from plugging those values into your equation, you will do a into your error. Let's say you're using L2 error. So L2 error is y minus y cap whole square divided by, I mean, summation divided by n. So that's a mathematical equation
Yeah.
because you will have y will be equal to alpha plus beta 1 multiplied by a
Yeah.
beta
Yeah.
2
Yeah. Yeah.
so on.
Yeah. Yeah.
So that equation, now you do, you differentiate that to get its slope because your beta 1 is a partial differentiation of that slope. So in each of the dimensions, it is gradient descent works by doing partial derivatives, and partial derivatives give you the slope, and that then um, my voice is echoing.
Yeah. Echoing. Yes.
Mute yourself, please. Those that are not talking, if you could mute yourself. Okay. So the by doing partial derivatives, you know how much delta to add or subtract from beta 1. So you start from an initial value, do partial derivatives, move along the slope. So reduce it along that slope, do a next step of gradient descent. Iteratively, you get that beta 1 value to
Okay.
some value where the
Okay.
error is minimal.
Okay. That is one. I have one more question. We
Yes,
were talking about association rules and also on collaborative, uh, you know, rules. There we were
filtering,
talking about the
collaborative
data
filtering.
size. You told me about the data size.
Yes.
Okay, if the data is less, you go on with association rule. If the data is more, you go with collaborative. So how do I define what is the size?
Good question. So there are people that there are formulae that if you have n data points in d dimensions, how many association rules are possible if your support
Okay.
confidence values are at a certain threshold. So
Mm.
that number, I remember that in the class I was showing a table. Let me just very quickly pull that table if I can get it. Um, just give me a second. I'll share that. Okay. I am pulling up our association rules, deck. And yeah, I think this is the deck, behavior modeling. Yes. And in this, there was a number of rules sheet. Uh, yeah, here. How many association rules are there? So if you see these numbers, by the time you get to 500 items, you have 10 to the power 238 possible rules. So, except for
Mhm.
smaller problems where, let's say, you're looking at, I don't know, one particular vehicle agency, people are buying cars and then there is after service that they are buying. Such things, association rules may be okay. But if you go to any reasonable sized,
I'm looking at a
yeah,
marketplace kind of
yeah,
a,
then collaborative
then it,
filtering.
yes, yes.
Recommendation algorithms. CF is one, but there are
Mm.
different types of recommend. I talked about, graph similarity. If you remember, we had a discussion.
Yeah. Mm.
So there are recommendation systems that are more recent than collaborative filtering. You could utilize them, but association rules will probably, not practical.
Sorry, Professor. You're saying I don't need to do collaborative filtering for going into recommendation, is it? I can use some other model.
Yes, yes. So there was a
Okay.
question in our class and whether collaborative filtering is the only way of doing recommendations. At that time, I said, I gave the example of LinkedIn.
Mm.
If I have a certain type of subgraph inside LinkedIn's massive graph
Mm.
connecting
Mm.
people, and if your subgraph looks very similar to mine, then
Mm.
LinkedIn might suggest to me,
By
why don't you
automatically, yeah.
befriend
Mm.
Mr.
Yeah.
Kannan? So that is not collaborative filtering. That is graph similarity that
Mm.
one is
Mm.
exploring there. So there are multiple ways of doing recommendations. I
So
think
for
that
this assignment, for the assignment, if I take this particular topic,
you can
I'll
do
go with
collaborative filtering.
collaborative filtering only.
Yes,
Okay. That
perfect.
was the reason why I asked all these. Correct.
Okay,
Thanks a
okay.
lot.
So it was a
Thanks a lot.
loaded question. Yes. So good. Any other questions before we close the class today? Okay, thank you very much for your participation. We'll meet next week. We have 2 classes next week on supervised machine learning.
Yes, sir. Yeah, good weekend.
Thank you. You too. Have a great
Thank
week.
you.
Thank you, Doctor.
Professor.
Good night, everyone.
Thank you very much.
Thank you, Professor.
Thank you.